start. Right. So can you see the slide? I'm showing slide number 81.
Yes, ma'am.
Okay. So if you recollect in the last class, basically we had started with steady state errors for various inputs given to the system. Various means three specific inputs were studied: the step, the ramp, and the parabolic input, right? And this slide that you are seeing is a summary of what we had studied in the last class. I mean, taking each um, input and the corresponding type of the system, we had tried to derive what the steady state errors would be respectively, and also in the process we had derived the what we call the error constants. So the position error constant, velocity error constant, and acceleration error constant values also we had seen what it would be, right? So over here now, this slide, as I told you, is a summarization of the same. So as you can see, if we apply a step input, I hope you can see the cursor. So if we apply a step input for a type 0 system to a type 0 system, then there will be a constant steady state error. So this is as per the derivation that we have already done, right? Just trying to summarize it. Similarly, if we apply a step input to a type 1 system, your steady state error is going to be 0. For a type 2 system, it's going to be 0. Steady state error is going to be 0 for the same input. Also, you can understand now that for systems of type 3 and higher, if I am applying a step input, the steady state error will still remain 0, right? On the other hand, now if we are applying a ramp input for a type 0 system, the steady state error is infinite, whereas for a type 1 system, the steady state error is a constant, and for a type 2 system, it is 0. You will see that for a type 3 and higher, I mean type systems, basically the error will remain 0. Steady state error will remain 0, right? Similarly now, for a parabolic input, we see that for a type 0 system, the steady state error is infinite. For a type 1 system, it is infinite. For a type 2 system, it is constant. We would be able to see that if you take a type 3 system, the error is going to become, steady state error is going to become 0. So you can see it's sort of following a pattern over here. So that way I was just off the hand, I was able to say that for a parabolic input, for a type 3 system, the error, steady state error is going to become 0. So basically, because it follows a pattern, you will also be able to extend for other systems as well as for other inputs, meaning that specifically instead of, I mean, your parabolic input, if you have an input which is say going to give you the Laplace transform 1 by s cube and sorry, 1 by s to the power 4, etc. So basically, and higher, inputs which are of higher order, you can say, when the Laplace transform is taken, you'll be able to see that it's going to follow the same pattern as such. But as far as the steady state error and error constants are concerned, they are defined specifically for the step input, ramp input, and parabolic input only. So the definition of Kp, Kv, and Ka are corresponding to a step, ramp, and parabolic input only. However, the methodology that we adopted can be applied to systems with types which are higher, as well as, if your inputs are basically following a similar pattern but have a higher order. uh, So now that was that, the table as well as the discussion that was done in the previous day was for unity feedback systems. So all that we studied over here till the last slide, I'm just switching slides, sorry for that, but yes, so it was, all of that was for a system where the forward path transfer function is given in some standard form and the type of the system is known consequently, because we can see how many poles we have at the origin, and that, that can be actually seen. But all the analysis that was done over here, all this was for a was for a unity feedback system. But what happens when we have a non-unity feedback in a system? We already know that systems may have a unity feedback, meaning that your feedback path element is only a pure gain equal to 1, in which case it's not put over here as a block, but it just, take the signal from there and take it to the feedback this way. Or it may be non-unity feedback, which means that there is a feedback element h's which is not equal to 1. It may be some other constant value, or it may have dynamics. So basically there will be a transfer function again for the h's. Now, as far as steady state error is concerned, if you want to find out the steady state error for non-unity feedback systems, then you cannot directly, use the same method that was outlined for the unity feedback system. Rather, you have to do something before you can apply the same principles. What do you have to do? Basically, that's written over here. So basically, for non-unity feedback systems, the first step that has to be adopted if you want the steady state error is that you have to convert from the non-unity feedback system into an equivalent unity feedback system. So you would recollect that we had done this exercise earlier, meaning that we already know that, say, for example, over here, if we have the forward path element as gs and the feedback path element as hs, now if we were to find the equivalent unity feedback system such that the forward path element is g equivalent is denoted as g suffix es, and there is a unity feedback. So this is the equivalent of this one. So we already have derived what the g equivalent would be. So now, if by, finding that G equivalent, if we are able to convert the non-unity feedback system into the corresponding unity feedback system, into the equivalent unity feedback system, then after the conversion, we can apply the same theory that we have, studied. Meaning that then, if we have this system, this is a unity feedback system, and here now we are able to access the error. ES is now accessible. Accessible means that we know that ES is equal to RS by 1 plus GES. So basically from there, when a step input is applied, when a ramp input is applied, when a parabolic input is applied, the error, steady state errors as well as error constants can be calculated, and you can actually find out those values as well. It is going to, after conversion to the equivalent unity feedback system, it is going to follow whatever is the standard one, that is this one. However, the conversion has to be done first. Otherwise, you will not be able to find the steady state error directly from this, that is from the non-unity feedback system. I'll tell you why, in fact, because over here, see, this point that you see is the output of the summing amplifier or the error indicator, whatever you call it. Basically, this signal is not the error. We have defined, or we define error as difference between input and output. But over here, this signal is equal to input minus hs into the output, right? So basically, it's not this signal when it's coming over here, it's not just simply the output, right? So that is why this is EAS, that is the actuating error, not the error. So basically, if you take the actuating error and then calculate on the basis of whatever, I mean, say, for example, if we are applying a step input, if you calculate the position error constant and hence the steady state error, it's going to become wrong. It's going to give you some values which are going to be wrong because you have not taken the error but only the actuating error. So the first step in I mean this analysis for a non-unity feedback system, if you are going to do steady state analysis and steady state analysis of what the steady state error is going to be, the first step to be adopted is that you convert to the equivalent unity feedback system. Then you apply the concept of steady state error and error constant after the conversion to this system. Now, one thing you must have noticed, but in case you have overlooked, is that when we have defined the type of the system, basically what do we look at when we see what the type of the system is? Do we look at the overall transfer function of the system or do we look at something else? I've said that, I mean, I'm sure you have noticed. Can you tell me what do we, I mean, look at when we are, I mean, trying to see what the type of the system is? Which transfer function do we look at?
Open loop transfer function.
Yes, right, very good. So the open loop transfer function means that this transfer function, that is GS or G equivalent is after conversion, that is the one that we look at, right? So basically, I mean, if we were to find, I mean, if somebody gives us, say, for example, a closed loop transfer function, and if you were to actually do steady state, I mean, analysis on it and find the steady state error, the first thing that you would have to do is, if you are looking at applying this table directly, I mean, okay, I will know the type and then I'll see what input it is, and accordingly I'll just, I mean, put the value from here. That's possible because once you have derived and got this table in front of you, you can put from here. That's acceptable. But what is essential is that you know the type of the system. So in case the closed loop transfer function is given, you have to actually find out the open loop transfer function considering a unity feedback. And then when you look at that GS, that is the open loop transfer function, you can see how many 1 by s's there are. And according to the order over there, you can actually say what type it is, right? So, I mean, if somebody, I mean, this is a question which people may try to put just to fool you, meaning that, okay, the closed loop transfer function is whatever. So that is given. And what is the type of the system? So you cannot directly say from there. What you have to do is you have to see what open loop transfer function resulted in that closed loop transfer function. That open loop transfer function, then you have to see how many 1 by s is, I mean, are there in that open loop transfer function, right? So anyway, so that was just to make you aware of that. So coming back to the non-unity feedback system, first you convert, then of course you can apply the concept directly. Now, this is a slide taken from, as you can see, Norman Nice book over here. Basically, we had, when we were doing conversion of a non-unity feedback system into an equivalent unity feedback system, we had said that there are several methods, one of which is given in this Norman Nice's book. So over here, you can see, basically, I had verbally, I think, tried to tell you or describe this method. So here, what they've done is they've gone by the method of block diagram reduction, unlike the one that you usually, I mean, apply. That is, you take the closed loop transfer function and then see how it is going to become equivalent to, if you consider some G equivalent over here. So you take both the closed loop transfer functions, compare, and then you get directly, algebraically, it can be got. That is fine. That's one method which is going to give you a correct result. But they have done an alternative method over here. That's just put on this slide for your knowledge or benefit, whatever. So here you can see what they have done is block diagram reduction method. So over here, first of all, in order to convert this non-unity feedback into a equivalent unity feedback, the last one, that is this one. In order to do that, what they've done is, first of all, they've added two signals over here, one with a -1 and the other with a +1. So, I mean, effectively, -1 and +1, when both of them are added over here, basically, you will find that this and this are equivalent, right? Next, what is done is they have combined these two together. So HS minus 1 is what they have, got. Combining the two, these internal ones, the ones which are in the middle, so-called. So combining these two together, they've got this, and then after that, what they've done is they've combined this one and that one. So again, over here, GS by 1 plus GS, HS meaning this would be the feedback path transformation that you have to consider then. Ultimately, after combining, they've left the unity value, negative unity feedback only separately. So here, after combination, it's going to give you the same result that we have already obtained. But nevertheless, this is another method. That's why I just pointed it out to you. There are, of course, other methods as well. You can use the signal flow graph or whatever. Methods are plenty, but of course, the final result is going to be the same. So anyway, somehow you have to convert the non-unity feedback system into the equivalent unity feedback and then go for the error constant. Okay, so this is just, first you convert, then the concept can be directly applied on the equivalent unity feedback system. Now, some observations. So this actually is based on the table that we saw earlier, 2 slides before this. So here now the same table is reproduced. Now, if you look at this table, it might give you some false ideas or some correct ideas as well. One thing that we are able to see is that as the type of the system increases, so this one, what do we see? We see that for a type 0, if it was constant, type 1 is 0, type 2 is 0, and higher ones, type 3 and higher types are also going to be having a steady state error equal to 0. Similarly, for a ramp input, for type 0, it was infinity. For type 1, it is a constant, type 2 it's 0, and then it's going to remain 0 after that. So basically, similarly for this one. So what we see is that as the type of the system increases, the steady state error decreases, right? So now, of course, this might lead to a false impression that, okay, then, if I design a system, I will go for a system which has a type which is high. Okay, so that naturally over there, your steady state error is going to be lesser compared to if you take, uh, another system which has a type which is smaller, isn't it? It's evident from here because, the higher you go on this side, the higher the type, the steady state error tends to decrease for the same input, right? Now, of course, yes, that is definitely correct in the sense that if you go for systems of higher types, the steady state error is definitely going to be smaller for the same input. Fine. But now, if from there, if you try to conclude that, okay, then I'll design systems which have higher type, then you are slightly mistaken, not slightly mistaken, in fact, grossly mistaken. Why? Because steady state error is not the only thing of concern. When we design a control system, steady state error would be one of the elements or one of the performance criteria in which we are interested. On the other hand, say for example, a system which has a small steady state error but has high transients, it oscillates a lot, okay, high over peak overshoot, etc. So you're familiar with these terms. So transient performance, if it is bad, then also it will be very, it's not going to be a system which is a desirable one. Now, I'll restate what I said in different words. What I'm saying is that if you go for a system which, say, for example, is of type 2. So if it's of type 2, what will be the minimum order of the system that you will be having? Either a second order or a third or fourth or fifth order if you have other poles as well, poles and zeros, of course. So, basically, for a type 2 system, the lowest order of the system that you can have is a second order and or a higher order system. Now, as the order of the system increases, what happens to other things? Other things meaning, number one is the transient response. The transient response will become more oscillatory when the order of the system increases. And if I increase the type of the system, automatically I have to, order definitely does increase, because if I have a 1 by s square in the your overall transfer function, minimum order that I can have is second order. Whereas for a type 0 system, The minimum order that I can have is 0th order, isn't it? Over there, the simple game k is also going to be of a type 0. I can have a first order type 0, which is k by s plus a, right? Still a type 0, but a first order, etc. So now, I mean, since the increase of the type automatically would be increasing the order of the system as well, basically, systems of higher types are not, I mean, sort of recommended, in the sense that it would be affecting the transient performance and also the relative stability of the system. If you have a step, if you have a system response which is highly oscillatory, it obviously implies that it is relatively less stable compared to a response which has lesser oscillations. Okay, and say for example, it oscillates for 2 cycles before settling to the steady state value, and a system which oscillates 100 times before settling. So naturally, you can understand that the system which oscillates more is obviously, I mean, less stable. Of course, stability can be understood by using several methods, some of which, in fact, you have not studied so far. Is in the other part, that is part two, of course, some of which you will be studying over there. Simple tests like Rauthovich criterion, as well as other, that is for absolute stability, or tests like Nyquist, I mean, criteria, or your root locus, etc. And also the Bode plot, which I think you have not done in the second year, but you have were supposed to do. All of those are tests for relative stability. So I mean, first, I mean, whether the stability has increased or decreased, you would be able to see by applying any of those methods. But nevertheless, I mean, for the timing, it would suffice to say that if the order of the system increases, the stability decreases, relative stability decreases. In general, I'm saying, and as a result of that, basically, it is not, you cannot make a sweeping statement that, I mean, if you have a system of higher type, it is better. It is better from the steady state point of view, meaning the performance, if in your steady state error is the only performance criterion that you are interested in that case, definitely, yes. If you have, say, for example, a type 1 system, you can just, I mean, put 1 by s and make it a type 2, such that your steady state error will be reducing to, I mean, by one order at least. One order, I mean, by one order, I mean from infinity to constant, or from constant to 0. So that is one order change at a time. Okay. So I'm just coming back to what's written on the slide. However, increase in the type of the system also increases the order of the system, thus making the system more difficult to stabilize, and consequently the dynamic errors tend to be larger. Okay, so dynamic errors mean the transient errors, errors in the, I mean, transient portion of the response will be much larger, and that also is not a desirable thing to, I mean, have. So basically, uh, you have to, of course, when people are doing the design of control systems, they would first of all look at which performance criterion they are more interested in, which one is less important to them, and then they would have to, I mean, trade off. Trade off means that you, I mean, sort of, you cannot have all the things, I mean, the best of all the things at the same time. So now you, I mean, see which one is more, I mean, sort of more precious to you, and then, okay, give more weightage to that, meaning that, okay, I mean, that is more precious to me, so I'll try to reduce that to a larger extent compared to something else which has, I mean, which automatically will increase a bit if I decrease the other one. So basically that is known of, known as something which is known as trade of, trade, and a hyphen in between, o double f, trade off. It has to be done. That is a general, I mean, method which is adopted by all designers, control system designers. But nevertheless, I mean, it would suffice to say that yes, though the steady state error decreases as the type of the system increases, it is not, I mean, it may not be desirable to increase the type always, because the dynamic errors would increase in that case. Now we come to a slide where, I mean, we have stated the limitations of error constants. So basically, I mean, it would appear that, okay, as far as steady state errors are concerned, I can apply, I mean, the concept and find the steady state error in all cases and so on. So that is why, I mean, a limitation slide has been put over here to let you know about what you can do, what you cannot do. So error constants do not give information on the steady state errors when inputs are other than the three basic types, meaning that, I mean, this table is valid only for a step or ramp or parabolic input, right? So if you have any, say, I have a sinusoidal input, then of course, I mean, I cannot apply the concept of the error constants, because error constants are respectively derived only for a step input, a ramp input, or a parabolic input. So basically, it will not be possible to find the error constants and hence any information on the steady state errors, at least by, I mean, applying this table. Also, another limitation of error constants is that error constants fail to indicate the nature of the transient errors. As we already spoke about it, we are able to find the steady state errors by using the error constant, but not the transient errors. By transient errors, I mean when you have a response, it will be, I mean, sort of having an oscillatory. In general, if I just look at a response, it will have a few oscillations going up and down, and then it's going to reach, it may reach a steady state if all goes well. So in that case as well, I mean, the transient portion naturally has a difference with the input that is applied. That is known as the transient error. So that is a dynamic error which is going to keep on changing as the signal goes, response goes up and down, right? So those cannot be, transient errors cannot be obtained by applying the concept of error constant. So that was the limitations of error constants and this concept that has been studied. So now we come to one example. In fact, I think I have another example. A few examples we will say of the application of the concept of error constants and steady state errors. So now you have to actually take out your exercise books and do these along with me. I think there are three parts to this question, and I would ask you to work them out. So I mean, read this out first. This is taken from the book by Norman Nice, as you can see. So a unity feedback system has the following forward path transfer function. It's given over here. GS is equal to, you can see, 10 into S plus 20, S plus 30, whole divided by S plus 25 into S plus 35. So that is your transfer function, forward path transfer function. It has been mentioned. Find the steady state error for the following inputs. So now you see that first it is 15 UT, then second is 15 TUT, and the third part is 15 T square UT. So as you can see, this UT, of course, is representing what? You're familiar with this, symbol, isn't it? Notation, I mean. What is UT? Signals and systems you must have studied.
Step input.
Yes, very good. So it's, I mean, it is a step input, but the amplitude is not one or unity value as we, I mean, usually, I mean, in fact, in our analysis as well, we had used a unit step input, but over here the amplitude is 15. So nothing, I mean, great about it. The only thing is that you have to keep in mind that whatever happens, the amplitude has to be taken into consideration finally when you are doing the analysis, right? So now, I mean, we'll go one at a time. So find the steady state error for the first one. That is, your input is now 15 UT. That is a step of amplitude 15, right? And your forward path transfer function is given, and this one. And it is also mentioned that the system is a unity feedback system, right? So now what you have to do is you would have to find the steady state error for this, that is 15 UT. Can you do it and tell me how to do it? What is the first thing that we will do? If, I mean, step input is applied, which error constant are we interested in?
Position error constant.
Very good. So we are interested in finding the position error constant. So Kp has to be found out. Now, if you recollect, what is Kp? Kp is equal to limit of GS as S tends to 0, right? So that now GS is given to you, you would have to find the KP, right? So can you do it and tell me what your KP value is?
Infinity.
Okay. So go to the next slide. Okay, so next slide is just a redrawing of the, not redrawing, a drawing of the block diagram where GS is there and unity feedback is there and you have to find that, okay. Next, yes. So what is Kp? That has to be found out. So Kp value is equal to, yes, you are correct, it is infinity, right? So that, I mean, this ESS now will be how much? How much means
0.
0, 1 by 1 plus Kp. So 1 by 1 plus Kp, where Kp is infinity. So the steady state error due to a step input is 0, right? So here, of course, I mean, because it's 0 and all that, the amplitude did not, I mean, matter. You did not have to actually uh, sort of think about what would happen to the 15 over there. But nevertheless, in the next one, of course, we would, I mean, would be having to have a look at the amplitude as well. So now the second part means your a ramp input is applied. So the input now that is being applied is 15 TUT, right? So since a ramp input is applied now, uh, which error constant are we interested in? The
Velocity error
velocity.
constant.
Yes, yes. So the velocity error constant is what we are interested in. So you have to find out KV and hence the steady state error due to the ramp, right? So how much is Kp? How do you find Kp? Kp is limit of SGS as S tends to 0. So those things you have to, of course, I mean, you have to keep in mind what Kv is defined to be. It was already said. So now how much is Kv?
48 by 7.
Let me check the other. Let me see. I think can you calculate the uh, this is given in this form. Is it matching? Can you say? Verify and tell me. 7.
Yes, ma'am.
It's okay, right? So basically, KV can be found out. Now, once KV has been found out, the steady state error due to a ramp. But now, of course, you have to keep in mind that the ramp has an amplitude 15. That's the only thing you have to keep in mind. So earlier, I mean, earlier meaning, I mean, when we were, I mean, defining the concepts, basically the steady state error is going to be equal to how much? 1 by kV. It was 1 by kV. But over here now, since your ramp has an amplitude equal to 15, it is going to be the that amplitude by kV, isn't it? So, did you understand what I said? Over here, the amplitude of the ramp is not 1, but it is 15. So, I mean, once kV was found out, you would recollect that the steady state error was found by calculating 1 by kV. That was for a unit ramp input that we had already done. So, over here, the amplitude of the ramp is 15. So, here, the steady state error due to a ramp, that is ESS for a ramp, is going to be 15 by the kV value. So, of course, you can verify and see how much, whether it's matching. It should. Tell me whether you can verify that.
Yes, ma'am.
Okay. So basically, I mean, that is how it is done. Next, of course, for the third input, which was a parabolic input, again over there, the parabolic input, I mean, the amplitude is multiplied by 15 units, whatever it is, right? So here again, since a parabolic input is being applied, the error constant that is of interest is the acceleration error constant. You have to find out Ka. Now, what was the definition of Ka? Ka was equal to limit of S square Gs as S tends to 0. So, Gs is given. So, how much is it?
0.
Okay. So, 0. So, now, I mean, you have to find the ESS for a parabolic input. So, you would recollect that your, I mean, steady state error corresponding to a parabolic input was given by 1 by Ka for a parabolic input with unity amplitude. So over here, there is 15 units of amplitude. Nevertheless, because it's zero, of course, it will not be consequential, but nevertheless. So now ESS will be found by, I mean, calculating 15 by KA, right? So KA has been found to be zero, so it's going to be how much?
Infinity.
Yes, that is put over here in the last slide. So basically, I mean, over here, the concept has been directly applied, apart from the fact that only the input amplitude is not unity, but it is something else, some other finite value, that is 15 over here for this particular example, right? So that was a direct example taken from the book by Norman Nice or Nice, whatever you call it. Now, a second example over here, again from the same book, that is Norman Nice's book, right? So just look at the example first. I mean, meaning look at the statement of the example first, then we'll work it out. So over here, the block diagram is given. Forward path transfer function is GS and feedback path transfer function is HS, right? So obviously, because it is a non-unity feedback, here instead of the error signal, that is ES, we have the actuating error signal, which is EAS, right? Fine. So now, I mean, in that block diagram, it is also mentioned that GS, that is a forward path transfer function, is given as 100 by S into S plus 10, right? So that is this one. And also Hs, which is of course non-unity, and also it is specified to be equal to 1 by S plus 5. So basically this goes to this block, that is the feedback path. We have 1 by S plus 5. So now, I mean, here the question is, you have been asked to find the value of the position error constant and the corresponding steady state error. So you may ask me, ma'am, you have not specified the input, right? Yes, of course, I have not explicitly specified the input, but here the information is hidden in the question itself. Can you tell me which input is being implied over here?
Step.
Very good. So because, I mean, as per the question, you have been asked to find the position error constant. Naturally, it implies that a step has been applied. So can you find Kp and hence steady state error? We'll go to that the next step. So what is the first thing that you have to do for this, I mean, system?
We have to know GE. That means
Yes,
we have to convert it for
very good.
unity feedback.
Yes. So the first thing is you have to convert to a equivalent unity feedback system. Just do that for me first. Then, of course, you have to find the Kp. Can you do it and tell me what you get? I'll give you some time.
Yes, ma'am. Calculated.
How much is it? Kp.
Oh, KP no GS. Okay.
Achha, G is, I don't think I have, nah. So you have to calculate Kp in order to verify.
minus 1.25.
Yes, I think it's something like that. Minus 5 by 4 is
Yes, ma'am.
1.25 it's going to be. Yes. So that is the value. I mean, try to think about what it means a bit later, and also the steady state error. So ES is how much is it going to be?
Minus 4.
Yes. Right. So basically, the value has been calculated for the position error constant, which is minus 5 by 4, and the steady state error is equal to minus 4. Now, the question, of course, will arise regarding what is the physical significance. So, I mean, what does a negative value actually signify? On purpose, this example has been put over here, as well as the book, Norman book also puts it, so that you, I mean, sort of understand a bit more regarding what to expect out of this concept, what not to expect. So, over here, this value, that is steady state error, is equal to minus 4, implies that, I think I have the, yes, implies that, okay, here this is the step input, that is the blue one over here is the input that you are applying to the system. On the other hand, I mean, for the same system, actually, I've done this plot by using MATLAB. It is, I mean, the green response is the actual response that you're going to get if you, I mean, excite the given system by a step input of unit amplitude. So the output, as you can see, is something like this. So apparently, it is as if, I mean, what would you normally expect if you're giving a certain input to the system? Naturally, the output, there will be some sort of, I mean, it's going to be a bit lesser. The output in the steady state would have been a bit lesser compared to the input, or equivalent, or rather equal to the input in the steady state. The most you could have had is that in the steady state it would have been equal to the input value. But over here we apparently have an output which is greater than the input, and that is sort of counterintuitive, right? But over here now, this axis is interesting. Interesting in the sense that I have not put anything over here in this axis because it cannot be done. Cannot be done means here I put units. Now, units means the respective or proper units, okay, as applicable. Now, if you have a look at the block diagram again, you will see, sorry, you will see that over here, okay, we are applying a particular input and we are getting an output. Now, because of this H's, that is a non-unity feedback in this particular case, what we have over here is that it is not essential that your output is going to be having the same units as the input, isn't it? Because here, I mean, the output multiplied by H's is going to be equivalent, having equivalent units to the units of RS, because you cannot subtract, say for example, if I have a voltage and a position, I cannot subtract it's going to be volts. But here the CS could have been anything else. It would be having a different unit. So apparently, I mean, the value that you see in the steady state in that plot over there, it apparently has a higher value. But higher value means what? I mean, say for example, 5 millimeters of position is what you have as your output on this side, whereas you have applied, I mean, 2 units of voltage here. So naturally, I mean, 5 will look greater than 2, but I mean, the units are not comparable and cannot be plotted or compared on the same platform, meaning the same graph paper, if you plot it, you have to show that, say that, oh, the units are different. Why different? You can see because here there is this feedback path transfer function Hs, which means that the signal over here and the signal over there do not have matching units, unless, of course, Hs is equal to 1, in which case now if this is equal to unity, there is no conversion factor. So directly CS will be subtracted from RS, which means that now RS and CS, for a unity feedback system, RS and CS will be having the same unit. And as a result of that, I mean, over there, the concept of steady state errors and error constants are much more meaningful. On the other hand, for non-unity feedback systems, though the same concept can be applied theoretically at least, but I mean, as far as the physical interpretation is concerned, you are going to, I mean, sort of land up with conclusions which may not be correct in the sense that, oh, the output is greater than the input. No, I mean, you cannot really compare between the output and input for a non-unity feedback because the units are different. So this actually, this example was given as a counter example. Method for calculation, of course, I mean, theoretically is okay, no problem with that. But I mean, if you try to interpret it, the interpretation will be, I mean, leading to wrong sort of conclusions, which is not desirable. So yes, the output is larger than the input, which means that the steady state error, if I do calculate, it's going to give you a negative value. But nevertheless, the units in the two cases are different, which means that I anyway should not plot it on the same graph paper like this, right? So numerically, of course, you will get values of steady state error, which may be negative as well. Though conceptually, it has, I mean, sort of no physical significance, because if the units are different, you shouldn't attempt to compare. So it is, I mean, as far as um, unity feedback systems are concerned, the concept of steady state error and error constants are very much applicable, and it gives you a feel regarding what is going to happen to the system, how closely the output is going to follow the input. Meaning that, say, for example, if I have a constant steady state error, I'm able to understand that my output will not follow the input. I mean, there will be always a difference between the output and the input. Or rather, if, say, for example, if I have the conclusion that my steady state error is equal to 0, I can safely say that the output value in the steady state is going to be exactly equal to the input value. So such concepts or such, I mean, conclusions are very much appropriate for unity feedback systems. However, for non-unity feedback systems, it would be safer not to attempt such, I mean, analysis. If at all, of course, numerically it can be done like I've shown you, but I mean, with the caution that you are comparing between different quantities and answers that you get may not always be physically significant. Now, we will do this, that is a ramp response of a second order system, which is of course a continuation of the same thing, that is steady state errors we are still doing over here. So ramp response of a second order, ramp response of a second order system is what we have over here. Now here you find that a block diagram has been drawn. Now as far as the standard second order system closed loop transfer function is concerned, can you find the closed loop transfer function of this? So we have over here in the forward path omega n square by s whole into s plus 2 zeta omega n, right? And you have a unity negative feedback as shown over here in the block diagram. What is the equivalent output to input transfer function over here? Meaning the closed
Omega
loop.
n square by s square plus 2 zeta omega n is plus omega n square.
Very good. So it is going to be omega n square by s square plus 2 zeta omega n s plus omega n square, right? Now, I mean, what we would be looking for over here is that we are looking, I am under the impression that in your signals and systems, you would have done the response of a second order system for a stepped input. You have done that several times, at least you were supposed to do it. I'm sure you've done it, right? So over here, we are going to look at the ramp response of the second order system. So now, of course, if you were asked to find the ramp response of a second order system, can you tell me the method which is going to be adopted? I'm not asking you to do it, but what, I mean, how would you find the ramp response? So input over here is what? It is, if I take the Laplace transform of the input, it is 1 by s. Ramp money 1 by s square, right? And I mean, I'm assuming that it has unity value, that is, the amplitude is unity. So that is given. It is a ramp input. I assume for, I mean, simplicity, that the amplitude of the ramp is, or the slope of the ramp rather, is equal to 1. Fine. Now, how do you find the ramp response? What is the method to be adopted? Just the steps I want. What will I do first? Then next what? Next what? I'm not asking you to do it. Of course, you would be able to do it if you know the steps.
So, ma'am, first we have to calculate CS, then inverse Laplace of that.
Yes, yes, very good. So not CS, CS by RS, that is, yes, that you have, and then RS is given as a ramp. So yes, then you get the CS, and then you have to take the inverse Laplace transform to obtain CT. So once you get the CT, naturally you would be able to see what the response is like. The mathematical expression is obtained. So naturally, if you want to plot it, you can plot it. If you want to keep it like that, you can keep it. So, yes. So, okay, over here, the procedure that we have stated is shown. I'm not asking you to work it out over here. Of course, you would be able to do it if required, I'm sure. So here the input is specified as a slope of unity slope, and Rs is consequently equal to 1 by s square. So Cs by Rs is equal to the closed loop transfer function, which you have already told me. And then Cs is equal to, so I mean Rs is given as 1 by s square. So that is this. So now from there, you what do? Break it up into partial fractions and etc. Method to be adopted, and take the inverse Laplace transform. So once the inverse Laplace transform is taken, you arrive at CT, that is the time domain expression for the output, right? So this is the final expression. I'm not showing the working out. You can, I mean, do it yourselves, I'm sure. Please try to do it and you will verify it. Not now, but I mean, in case you have some difficulty, you can tell me. So CT for this particular, I mean, system that we had, this one is given by, is equal to, after working all that out, taking the Laplace inverse, it happens to be t minus 2 zeta by omega n plus this portion. I'm not reading it out, for zeta lesser than 1. So now, I mean, you can see the overall expression for the output, right? So this is the output expression for the output. Naturally, if you want to plot it, it can be plotted, fine. But now, I mean, if you look at this expression, what are we able to see? First of all, this response over here has three distinct uh, parts in the expression, one of which is the t. It's, I mean, a standalone t over there. The next portion is the minus 2 zeta by omega n, which is, of course, a constant, right? And then the third portion, which is this one. So now let us inspect this, I mean, a bit more closely. So of the three things over here, the first, that is t, first part of the expression, that is only t. What does it indicate? What will be the response if I just say Ct equal to t? What will the response be like visually? Visually means if I plot it on a graph paper, what is it going to look like? Is it going to be a constant? Is it going to have some slope? Is it going to be
Ramp.
parabolic? Right. So this portion, that is Ct equal to t only, this t over here would give a, I mean, would be following a ramp like this one. Okay, so over here, and just the things are not visible. I don't want to see at this time as well, but you can see that there are two axes over here. This axis is obviously the time axis. Here is the output axis, right? Output or input, whatever is being plotted. So this t over here, now if I were to plot on this, I mean, graph paper, it's going to be a ramp, right? Now the next thing is minus 2 zeta by omega n. So here now, if say for example Ct was equal to t, it would have followed a pure ramp which was passing through the origin, right? The straight line passing through the origin will be having the this I mean response Ct equal to t. But if somebody says okay, Ct equal to not t but Ct equal to t minus some constant, so what will that imply? It would imply that what would it imply?
Error.
Error, yes. So I mean the output is not going to be following the I mean the first ramp that we spoke of, that is the ramp which actually I mean starts at 0 and then goes up with the slope. But I mean there will be a constant difference with that ramp, meaning that the ramp will be closely followed, but at each point in time there will be a slight difference, and for that matter the Ct will be lesser in amount compared to the ramp, meaning that if I were drawing the ramp itself and then I mean drawing this, that is Ct equal to t minus this constant, then I mean that would have been slightly, I mean there would be a difference with the original ramp, and for that matter the difference would be such that the output would be lesser compared to the input ramp that I was speaking of, right? Then we have also in this response a third portion of the response. So this third portion of the response is also very interesting in the sense that here now we find that this is basically this portion. If I describe it verbally, this I can see is, I mean, within the square bracket. So sine of something, right? So it is a sinusoidal, I mean, quantity over here, but that sinusoid has an amplitude which is described by this, right? So now, I mean, what does that imply? This is this whole, I mean, third part of the expression is a sinusoidally varying quantity with an exponential envelope, right? And what sort of exponent is it? It has a minus sign over here. So e raised to the power of minus something and into t, right? So what, I mean, sort of envelope could this be? How would I describe it? It would be an exponentially decaying envelope because, I mean, because of that e to the power of minus something. E to the power of minus something means what? It's going to be having a decaying characteristic. So here now, I mean, if I look at the overall expression, expression, only this third portion is going to be sinusoidally varying, but the amplitude is going to be following an envelope which is sinusoidally decaying. So now over here, if I look at the overall expression, the expression tells us that we will have, I mean, a response which is, I think, drawn in it's a bit better, but bigger, I mean. It is going to be having a transient, okay, I have not told you about the transient portion, I'll come to that in a moment. There will be a sinusoid which is going to be decaying, having a decaying envelope. So that portion is this one. Let me go back. One thing I missed saying. Now, I mean, okay. So this is a sinusoidal quantity with an exponential envelope, and for that matter, an envelope which is exponentially decaying, right? Now, as t tends to infinity, what happens to the envelope? This is your amplitude of the sinusoid, right? So how much will be your, I mean, value as t tends to 0? What will happen to the envelope? How much will that value become? As t tends to 0, I am asking about only this portion. কি বললাম t tends to 0 বলছি না, sorry. I want you to answer what is going to happen as t tends to infinity. Steady state value চাইছি.
Exponential term will be 0.
Yes, exactly. I think there was a slip of tongue. I realized that later. So basically, I want the steady state value. Steady state value means that as t tends to infinity. So because it is e to the power of minus some constant into t, as t tends to infinity, this term will reduce to 0 because 1 by a large quantity will be actually 0. So that it means that the envelope of the sinusoidal quantity is going to be 0, which means that this, I mean, whatever sinusoidal, I mean, variation was taking place, that, I mean, variation was actually, I mean, sort of decaying within an envelope which was exponentially varying. And finally, as t tends to infinity, that sinusoidal quantity will vanish because the envelope is going to just reduce to 0. So whatever variation is there will be in the initial portion, meaning the transient portion of the response will have a sinusoidal quantity within an envelope which is exponentially decaying. However, in the steady state, no trace of this sinusoidal quantity will be found. Okay, so I mean, in the steady state, what will happen? Sorry, happen to CT? It will follow the ramp, of course, minus this, and then plus this portion will be a 0. So in the steady state, CT will be just, I mean, following this portion. Okay, steady state means as t tends to infinity. So basically, if we look at the response, we are going to see a similar thing because this is a bit bigger. I'm showing you this same response that I had on the previous page, but it's a bit bigger. You can see it. So here you find that there is a sinusoidal variation over there, and you can see that that envelope is actually varying, though it's, I mean, sort of a bit, the envelope is small, amplitude is small, so that, you can see smaller variations over there, but you can see that it's going down and up and all that. And then finally, say for example, after this equal to 9 seconds or 10 seconds, whatever, 9, 10, 9.9 or 1 second, say after 1 second, you find that the difference with the input, this is the input ramp, the top one, and the response is this, that is the bottom one. So you can see that the difference of the response with the input ramp, it remains constant thereafter, right? So that now, you can say that in the steady state, there will be a constant steady state error over here. So from this response now, if I were to find the steady state error, first of all, in the steady state, t tends to infinity, fine. And if I were to find the steady state error, it means steady state error was, supposed to be equal to what? First of all, I will take the difference between the input and output, right? So my input was t. The output is t minus this plus this, right? Then I take the limit as t tends to infinity. So, when I take the difference, this first, the initial ramp is there in the input and the output, so it cancels out. The second portion, of course, will be there, and the third portion as t tends to infinity becomes 0. So that finally, what is the value of the steady state error that we get? We will get 2 zeta by omega n, right? So this was, of course, the roundabout way, meaning the, sort of the conventional way, of course, going from the time response and then making t tend to infinity to find the steady state error. Now, alternatively, of course, it could have been done by using a second method, which is a it's worked out. Second method, which is basically, instead of taking the time domain expression, the same thing you do in the frequency domain, that is in the S domain. So over here, what is being done is that you can see, to find the steady state error, the final value theorem has been applied, right? So final value theorem on what? The difference between the input and output, that is the error, right? So SES as S tends to 0 is what we have over here. So from here now, CS has been directly put instead of working with CT, which was, slightly more complicated. And in that case, you need to find out the Laplace inverse. Here, in this method, you need not find the Laplace inverse from the, transfer function itself. You can do this. So here now, after working this out, again, you will come at the same value, which is the steady state error, which is equal to 2 zeta by omega n, right? Now, this is the alternative method for calculation of the steady state error directly from the in the Laplace domain. Now, of course, the third method, meaning the one that we have just done earlier to this, previous to this. Now, okay, we've come back to the same system, which is a which is a second order system with a unity feedback. It's a standard second order system with a unity feedback, and a ramp input has been applied. Now, from the concept of steady state error and error constants, if I ask you to find the steady state error, what would you do first? Should I repeat the question? You have this system given to you, and you have to find the ramp. You have to find the steady state error to a ramp, right? So for that now, I'm asking you to apply the concept of steady state error and error constants. Apply the concept of error constants and hence
So
find the
first
steady
we
state.
have to know kV.
Very good. So because it is a ramp which is being applied, you have to calculate kV. So you can do that. You can see the GS, that's the open loop transfer function. What is kV going to be
Omega
equal
n
to?
by 2 zeta.
Yes. So kV will be limit of SGS resistance to 0, which is omega n by 2 zeta. And then once you get kV, your steady state error will be 1 by kV, which is what? 2 zeta by omega n. So you can see that, I was verbally able to, you were verbally able to actually, just with minor, sort of calculation, you were able to find the steady state error directly by applying the concept of steady state error and error constant. Whereas if you did not know about that concept, you would have had to go either by the two methods, either of those two methods would have had to be applied, meaning that either you go in by the method of calculation of the time response and then the steady state error, or you go by the method of this, that is at least over here as well, it's going to take at least 2 or 3 steps or 4 steps before you arrive at the steady state error value. However, by direct application, by directly knowing that if I have a RAM, I find out the kV, and then 1 by kV is going to give me my steady state error. So directly I'm able to find the steady state error. So that was okay. So the same method, that is method of steady state errors, has been shown over here on this slide. That is, you find kV because the ramp input has been applied. So it happens to be omega n by 2 zeta, and then the steady state error is 1 by kV. So you directly get it. I think that is the last slide. Achha, before finishing off, can you tell me something, that is, how familiar are you with Bode plots? Has it been taught at all in class? Do you know, I mean, to draw Bode plots and interpret?
No, ma'am.
No. Okay, so
ম্যাম
in that
কিছুটা
case,
জানি,
কিছুটা জানো? আচ্ছা, মানে তুমি নিজে পড়ে জানো না ক্লাসে করানো হয়েছে?
ক্লাসে করা
নিজে
হয়নি ম্যাম।
পড়ে, ক্লাসে করানো হয়নি।
ক্লাসে করানো হয়নি, ক্লাসে করানো না হলে অসুবিধে। So what I'll do is, actually there was a portion added to this, that is the sort of link between steady state errors and some of the, I mean, some interpretations which can be done by using Bode plots, but it is not very sort of, I mean, relevant in the sense that we cannot, I mean, apply the concept that, I mean, I was about to tell you. You cannot apply it globally. So what I'll do is I'll skip that portion. That is, I'll show you what I'll skip. Steady state error from the frequency response, meaning the Bode plot, is what we had over here. So Kp, Kv, and Ka can be found for specific system types. Kp for a type 0, Kv for a type 1, and Ka for a type 2 system by using Bode plot. I will not go into this portion here directly, but nevertheless, I mean, we'll go into system. I mean, we will go into the next module that I have over here directly. But I mean, after completing a bit of the syllabus, there will be something which is known as compensation of control systems, before which I would have to sort of either recapitulate or revise whatever. If it would have been earlier, that would have been the term I would have used. Otherwise, if it has not been done at all, I will try to give you an outline at least of how Bode plots are plotted and interpreted. And that will be then, before going into compensation of control systems, I will be doing Bode plots in brief, maybe half a class or 1 class, so that you are able to understand the concept of compensation better. But right now, I'm skipping this portion because this actually is, you will not miss much if I do not teach you this small portion which is over here, because just to teach this, I do not want to go digress from the main stream of what I am supposed to teach. So the next thing I'll be teaching is over here. Okay, before going to that, you have already got the PDF of the slides. There you will see that at the end of that Bode plot portion related to the steady state errors, after that you have exercise 1, exercise 2, and the first one has 5 parts and there is the second one. So anyway, so please, I mean, work out these exercises and give me feedback. I mean, whether you were able to do it. If you have confusions, ask me in the class or email to me. If I get any email of that sort, I may discuss in class as well if required. So you are going to work out the 2 exercises which are given at the end of this, steady state error and error constants, and let me know if you have any difficulty or if it requires some sort of discussion. But in the next class, we will be starting with control system components. This is what we are going to do. Okay, so I'll stop the recording right now. But Bode plots, of course, will have to be done. It is going to be done, but not now.